actually graduated this semester. I started my course in course for PhD in UTD at 2016, so that's 5 years and a half. And what I'm going to talk about is the title is over there. It is a piece of my dissertation study. So the focus of my research is based on sparse recovery. It is a problem that is formulated like this. You see this everywhere. It is AX equals to B. It's basically a linear system. The property of the system I am interested with is that when X is having a relatively small number of non-zero elements. Techniques for solving this type of problem can be have many names: sparse recovery, compressive sensing, compressed sensing, and many other names. Methods used for this type of problem, there are many of them, and I studied some of them and used them in different applications. So the first type of application is uncertainty quantification. What happens here is that basically we have an unknown system, but we model that system using different kind of bases of functions. Here, what I choose is orthonormal polynomials. And the goal is that we have an unknown system. We give an input. That kind of a black box system will give us some output. I use that. I project them onto the basis I choose. And I find out the coefficients for the system under that basis. And the techniques I choose to use is to use compressive sensing techniques. So I want the system to be with as small number of coefficients as possible. That will turn out into a linear model like this. With some techniques, of course, you need to make sure that you actually do have a system that is having small number of non-zero coefficients. But I will skip the details of those techniques here. That'll be complicated to talk with. And I will show one example here. We have a KdV equation. This is the equation that used to describe shallow water waves. It has soliton solutions. It has many different kinds of soliton solutions. And I describe them using a random field like this. And I choose a solution that is having the majority of the singular values here to be a few small, the largest the first few singular values takes the majority of the singular values. And the solution can be expressed by this. And I perform some, since this is expressed by a random field, so I perform some simulations to achieve, to do a measurement of the coefficients I recovered from those methods, from the compressive sensing methods, and the accuracy is presented here. The dashed line here is the kind of the state of the art of the techniques, and the solid lines are what I recovered using different compressive sensing techniques. We see some of them performed well, some does not. And the second application I use is SAR imaging. So basically that is using radar to form an image of the target area. Well, radar is using electromagnetic waves. So I start with the Maxwell equations. This equation 7 here is by taking the curl of the electric field. And then after some simplifications, you can achieve this. For people familiar with PDEs here, you may see that this is actually a wave equation. After some approximation, simplification, we can solve for the scattered field given as this integration. And this equation here can be represented as a linear equation. And then similar techniques can be applied to form an image. So I performed some experiment by using this setup. And I achieved a recovered image here. So the first image is the traditional SAR imaging technique. So following the Shannon-Nyquist sampling rate. These two are using different kind of regulations for compressive sensing, and they take roughly 25% of the data I collected from here. Visually, you do not see any difference. Detailed analysis of the resolution and the point quality, I will skip here. The basic point is that I use 25% of data, I achieve similar results. Some of the results is actually better than the original method. And then I build up acceleration schemes for compressing algorithms. And I prove the acceleration schemes using linear examples. So you may see that this is the classic conjugate gradient algorithm. And this is the another classic acceleration scheme of the gradient, which is Nesterov. And this is FISTA, which is one of the acceleration. Oh, sorry. This is FISTA, one of the acceleration algorithms that is very usually used in compressive sensing. And you can see that it utilizes what we have seen here as Nesterov accelerated algorithm. So my idea is to combine this and conjugate gradient. I developed a new algorithm to accelerate the algorithms for compressive sensing, and I tested them on quadratic problem and proved actually it has acceleration on this type of problems. And that's basically my research. Thank you all.
Thank you.